Welcome to Tiny Show and Tell Us, the bonus series where you write in with your favorite science news or factoid, we read your email aloud, and then dive deeper. I'm Sam Jones, and I'm here with my co-host, Deboki Chakravarti.
Hi, Sam. Last time we talked about biodegradable superglue and a super potent greenhouse gas in high voltage equipment. So if you want to have your really exciting science thing that you learned about featured,
yes,
please send it to us. We love reading your emails and going through them. All you have to do is email tinymatters@acs.org or fill out the form linked in the episode description. Okay, Sam, I'm going to start us off today.
All right, I'm excited.
I am here to talk to you about a really cute mouse.
Oh.
But also a little bit of a twist. So this is from listener AJ, and they said that I saw this story on Last Week Tonight, and the little guys are just delightful. There's some interesting implications on what bringing back previously extinct species can mean for ecology.
Ooh.
So I've just read all of that aloud. What we're talking about are these really cute woolly mammoth mice that some of you might have seen. They have this long, woolly, golden fur. They're kind of a little bit plump.
To me, they look a little bit like Chewbacca mice or something.
Yeah, right? I had guinea pigs growing up as a kid.
Yeah.
And it kind of reminds me of some guinea pigs because they have really weird, funny fur patterns.
Yeah.
It really reminded me of that. So this is the result of work from a company called Colossal Biosciences, who engineered mice with characteristics from a woolly mammoth. So the way they did this is they went through the mammoth genome and they compared it to DNA from the closest living relative of mammoths, which are, probably not surprisingly, the African and Asian elephants. So what they wanted to do is they wanted to find genes that would feel very distinctively mammothy. And some of the ones they landed on were genes that encoded long woolly hair and also being able to metabolize fat in a way that would have helped the mammoth survive the cold. So they found those genes and then they were like, we want to see, can we get other genes in other animals to be more like this? So they went into the mouse genome to find genes that they could modify to make them more mammoth-like.
Okay.
I have quite a bit to say about what I think about this work.
Yeah.
And most of it is critical. But I do want to say here that I think this approach on its own terms is interesting. I don't know if this is the most interesting application for it. Overall, I like this idea of digging through different genomes and comparing them, figuring out how we can modify one to resemble another. I can imagine a lot of purposes for it in medicine, the production of small molecules. I think there are really, really exciting applications out there.
Yeah. I mean, transgenics, introducing genes from one species into another,
right,
is so much of what is done in biomedical research.
Exactly.
Introducing human genes into mice.
Yeah.
So that you can actually get a better idea of how drug activity would actually be in a human versus just a mouse. So
yeah,
I agree. I think on the surface, this kind of stuff is really important to be able to do for research. But yeah, I have questions.
Oh, we'll get there for sure. So with these mice, what they did next after they figured out kind of what changes they wanted to make to the mouse embryo, they then genetically modified those embryos and put them in female lab mice, and you get these cute woolly mice.
And these mice were like, why does my baby look like this?
Yeah, I know.
This baby doesn't look like me or the dad. What is going on?
Yeah, so I think about this a lot because what they want to do next, this is a way I think to prove that they can do this.
Yeah.
But their real goal is to actually move on to editing the genes in Asian elephant embryos and then implanting them into female elephants so they can make babies that look more like mammoths. And I have questions about
I have questions too.
What a mother elephant is going to think about her baby coming out and looking very different.
Yeah.
Mammoths and elephants just live in, I assume, in very different climates, right?
Yeah.
I don't think that's a bold assumption to make, right?
No. That makes me kind of feel sad for this hypothetical woolly mammoth looking elephant baby because then it's is the mom not going to take care of it?
Right.
Is the herd not going to look after it?
Yeah.
Oh, it's making me sad. I think I'm just too pregnant right now to do this episode.
What if you gave birth to a woolly mammoth baby?
See, I'd have questions. I would love it, but I'd be like, how did this happen?
Yeah. Man, we could talk all day about this. There's so many questions. It comes up so clearly here because elephants are such social creatures.
Right.
And so there's so much to being an elephant and I assume to a mammoth. I mean, really to any animal that's you could argue this point. There's a way in which the foundations of that may be laid in the genome, but there's so much more to it than just the genes themselves.
Right.
So you're never really going to be resurrecting the woolly mammoth. You're going to be making a version of a thing. Right.
Right. Yeah, exactly. You're not resurrecting something. You're resurrecting certain genes, let's
Yeah,
say.
exactly. Yeah. They're also working on the dodo and Tasmanian devil, but if the name Colossal Biosciences sounds familiar to people, that's because they're also the group behind the recent hubbub around the supposedly de-extincted dire wolf.
Right.
The dire wolf went extinct 12,000 years ago. People love talking about dire wolves because of Game of Thrones.
Right.
And at least the way that the research got communicated to the public, it seemed like the claim was that they had made a dire wolf. They didn't make a dire wolf. They actually just made gray wolf hybrids. They made some changes to the genes so that the pups would look dire wolf-ish. They made around 20 edits in 14 genes. But at the end of the day, they're still a gray wolf.
Right. And I do wonder, I want to see follow-up on that too, because now I have questions about, how are they fitting in with the other wolves?
Yeah, right. So these projects, like what you've been talking about, they fall into the grand scheme of de-extinction work, which is pretty controversial, and I think for good reason. One of the big questions is, is this even the best use of resources when it comes to the idea of conservation, right? Some of the supposed argument for de-extinction is a conservation argument around bringing back animals that went extinct possibly because of human behavior. But we have a lot of critically endangered species right now, and it's hard enough to implement the programs to protect them. So what does introducing a new species in this way, supposedly, if you actually were introducing a new species, is that the best use of resources?
And also, how would it not just go extinct again?
Yeah.
That's my big thing. I'm like, okay, yeah, let's say somehow you de-extinct the woolly mammoth.
Yeah.
How's the woolly mammoth gonna continue to survive? We just have another highly endangered species on our hands.
Yeah.
It's cool. It would be crazy to have that come back, but at the same time,
right.
What would happen to it? And would it just go extinct again along with all the other species that are on their way out?
Right. And I think that's related to another big question, which is could these animals even exist in nature the way they did when they were originally around? The planet has changed, the climate has changed. And first of all, they're not even coming back. This isn't we're digging up a woolly mammoth from the ground and bringing it back in a time machine, right?
This isn't Jurassic Park.
This is a new animal, but it's built for a different age. It's just going to be so different.
Yeah.
We talked about this too. There's just this bigger question around the ethical considerations for animals. I don't think either of us are opposed to animal research, but there's just so much that has to go into it to make sure it's being done ethically. And it's really uncomfortable to me to be making a new species via another species in this way. With all of that said, I do want to say that I don't find these big de-extinction projects that compelling. I think the ethics and the utility are questionable, and also scientifically, like I said, just not the most interesting application of the techniques going on. But I do think there are interesting de-extinction projects. They're just much smaller in scale. I think for one example, we talked to Nadine Zimmert for one of our recent episodes about evolution going backwards. And one of the things that she and her colleagues did was basically resurrect an ancient antibiotic. They went through the genes, they figured out what this antibiotic would have looked like. And that to me is so much more interesting because it teaches you about how antibiotics evolved and how they work. And it can help us with understanding other challenges like antibiotic resistance. So
it's super applicable.
Exactly.
Super duper applicable.
Yeah. And it's just, I think the compelling projects are actually often much smaller in scale, in part because you don't have to do as much. You don't have to do the full woolly mammoth to make it what you're claiming it is. But also there's just so many interesting questions that can happen when you let things be small scientifically, I think.
Yeah, I agree.
Which is why we're Tiny Matters.
Exactly. Well, that's super interesting. Thanks for getting into all of that because I think it's a fascinating conversation. So my tiny show and tell us is from listener Tim, who wrote in saying, I wanted to ask, with the matter on boiling water and breaking down or capturing microplastics, do things like my carbon filter help with capturing those particles? Are there any other known methods to reduce or eliminate them from our food or water sources? Good questions, Tim.
Mm-hmm.
So first off, I think Tim is referencing something that I think I talked about it in a tiny show and tell at the end of an episode last year, which was a study where scientists boiled tap water and then filtered it to remove nearly 90% of microplastics. The catch was that the water had to be, quote, hard water, meaning it had high levels of calcium carbonate. So that was sort of trapping the microplastics, and then you could filter it out. Not everyone's water contains a lot of calcium carbonate. And also boiling your water every time you want to drink.
Right.
Yeah, it's laborious. Tim then mentioned his carbon filter. So activated carbon, it's super porous. It uses a process called adsorption. So not absorption, adsorption, where molecules will actually stick to its surface because it has a huge surface area and they get trapped. And so as for, if a carbon filter is good at capturing microplastics, they do seem to remove some microplastics, but they're not great at it. So I did a little digging and I found a study from 2023 that looked at a number of methods, including activated carbon, as well as ion exchange and microfiltration. Ion exchange filters, they're made up of this resin that's covered in charged ions. And those charged ions are harmless. They're things typically like hydrogen or sodium or potassium, I think. And so as water passes by, unwanted ions like lead will be exchanged for those harmless ions and stick to the resin, which is really interesting and I think a very complicated process that I'm not going to get into, but it's kind of interesting and makes sense why you'd call it an ion exchange filter because you're exchanging ions. Ideally, the harmful get trapped and the harmless are just released into the water. But the problem is that microplastics aren't typically charged, so ion exchange filters are going to be less effective. But then the third method that this study looked at that I mentioned was microfiltration, which is very good at removing microplastics. So microfiltration, it's a category of methods, but essentially you're using pore sizes that are typically between 0.1 and 10 microns. In this study, they used a filter that was about 0.2 microns and then a little bit larger than that. And the way microfiltration works, it's super simple. It's essentially just stopping anything bigger than that pore size from passing through, which does include a lot of microplastics because microplastics can range from a nanometer to 5 millimeters. A nanometer is, of course, much smaller than a 0.1 or 0.2 micron filter. 0.1 microns is 100 nanometers. So this method is not perfect, but it still captures a lot of that microplastic range. So this study ultimately looked at a combo of activated carbon, ion exchange, and microfiltration. And in combination, they were really, really effective at removing microplastics, like 95, 96% sometimes, like up to almost 100%. But really, it's microfiltration that seems to do the best job. And also, who is going to go through the process of buying and using all three in combination? It's just, that's a lot.
Right.
So, some microfiltration systems are very expensive, some less so. But they are definitely far more expensive than your standard activated carbon filter that I think a lot of people have for filtering their water. So I just thought it was really interesting. And ultimately, it just comes down to how small is a microplastic? Can we filter water in a way that just traps it?
Right. Do you know how long the microfiltration takes? Can you just pour water through it or do you have to push it through?
That's a great question. I think it definitely would depend on how tiny the hole is.
Right.
If you waited long enough, the water would come through.
Yeah, right, yeah.
And I do wonder if you push it through, if that opens up the pores a little more than you'd want. You know what I mean?
Yeah.
I'm not entirely sure if they pushed it through. They kind of just said
you can use it.
When we applied a microfilter kind of thing. Yeah.
Because I'm just imagining sitting there for an hour and just watching one drop at a time.
I just want a glass of water. No, there must be. I mean, these microfiltration systems you can get, for sure there's some sort of pump situation in a bunch of them. It must be going through faster than you would think. If you were just let's let gravity do its thing. I think that it could be a long process.
Yeah. Well, that's really cool. That's interesting that there are these different methods, even if some are clearly not that great.
Yeah, I did think it was interesting though, because I have heard of, these ion exchange filters.
Right.
And it is interesting to know they don't seem to be better really than activated carbon because again, you need molecules that are charged. You're removing stuff that would be charged and microplastics typically aren't. So maybe it's trapping some, but ultimately the tinier the pore size, the better your chance of removing microplastics.
Right. Well, thanks, Sam, and thanks to EJ and Tim for submitting to Tiny Show and Tell Us, a bonus episode from Tiny Matters created by the American Chemical Society and produced by Multitude.
You can send us an email to be featured in a future Tiny Show and Tell Us episode at tinymatters@acs.org, or you can fill out the form that's linked in the episode description. And we'll see you next time.